All right, so unfortunately, the recording didn't work on Monday, so I'm just going to start with a review of master equations. I've written it up here so everybody can see it, but we'll just walk through it here. So first of all, let's think about what master equations are. So if you get one thing out of master equations, I want you to remember what they are. And they are a system of ODEs that describe the dynamics of the probability distribution. So if you have 100 different states in your state space of your discrete probability distribution, you're going to have 100 master equations and so forth. So you have one master equation per discrete probability category. And so the differential equation for a specific one of these master equations, the nth one, is given by this sum, where you have the probability of going from state J to state N times the probability of being in state J to begin with. The important thing to remember is that the quantity Q and N, I just got started a little early, so yeah, so the quantity Q and N here is going to be negative because it is the diagonal element of your transition rate matrix. So by definition, it describes the flow out of that class. So you'll capture the flow out and the flow in. We talked about one specific example of a master equation that was motivated by the SIS epidemiological model. And for the remainder of this section, when we talk about continuous time discrete state stochastic processes, I prefer to write them in the form of a table like this because I think it's easier to think about. So we have two different types of events. We have transition events and recovery events. And then we want to describe the rate at which each of these events occur. So you have beta SI, where I normalize beta by the population size kappa. Since this is an SIS model, S plus I has to sum up to be the total population size. So I can always exchange the S for kappa minus I and only follow the number of infected individuals. So I only have one dimension in this model. And if I have a transmission event, it decreases my number of infections by 1. Wait, this is backwards. I'm sorry. It increases the number of infections by 1. And if I have a recovery event, it decreases the number of infections by 1. All right. Note that this table is just a way of writing the transition rate matrix. So you could have written the transition rate matrix. It's a diagonal matrix where you have the diagonal element, which is the flow out, the upper triangle, the upper diagonal, and the lower diagonal. But these events are exactly the same as those events. But either way, these are the rates that you're going to use for your master equation. So we have the rate of change of the probability of being in state N. So we think of the flow out, which is given by this quantity here. I think I was trying to smush everything into one line and skip the term. So we also have plus gamma N. Then we have the flow in from below and the flow out to the state up above. So that is how we connect the continuous rates to these master equations. Is there any questions about this? All right, so that is the master equation approach. To practice it a little bit more and to illustrate how this can be extended beyond some of these simple stochastic systems, let's consider a little bit more complicated example of the SIR model. Okay. So what do we have here? Well, we have this table again where you write the event that occurs, And in this case, we have just a transmission event as well and a recovery event. So the events themselves didn't change. The rates do change slightly. So it's beta over kappa S times I and gamma times I. So at first glance, these look the same as before, but I can no longer exchange this S for kappa minus I because I have an R class. So I'm going to actually write my R class as kappa minus S minus I, and I'm going to ignore the R class, but that means I can no longer ignore the S class. So these rates now depend on two variables. And then I want to talk about the change, the effect of each of these events on the states. If I have a transmission event, it decreases the number of susceptibles and increases the number of infected individuals. And if I have a recovery event, it decreases the number of infected individuals. So I can no longer describe this with a simple master equation. I have to introduce two variables into my master equation. So I want to follow the probability that I have n susceptibles and m infected at time t. So this is the probability of n susceptible and m infected at t. All right. So there could be a lot of these equations. If I had 20, a population size of 20, how many equations would I have? Any guesses? It's very close, actually. So you could, at the first pass, you could imagine having to follow the number of susceptibles between 0 and 20. And you could imagine having to follow the number of infecteds between 0 and 20, in which case you'd have something like 21 times 21 equations, or which is approximately 400 equations, right? So that would be the first pass. But I think your intuition comes from the fact that n plus m has to sum up to being kappa. So one way of thinking about that is the lower triangular of a matrix where you have n plus m sum up to k. And so, or less, k or less. And so in that case, it actually turns out to be 21 choose 2, which is approximately 200 equations. Okay, so we have a lot of equations here. So this is one key limitation of these master equation approaches, that even with an astronomically small population size of 20 here, we can't really follow the full dynamics. Now, of course, if the population size got pretty big, we could just use a deterministic approach instead. So we're usually interested in cases when the population size is pretty small. But just be aware of the fact that you might have lots of equations. All right, so let's try to actually write down what the differential equation is here for this quantity. All right, so I'm gonna let you guys give it a try, and then using the principles that I just outlined, and then we'll do it together. All right, so hopefully everybody's gotten a chance to at least get started Can somebody give me one of the terms that we have to have in our differential equation here? Go for it, Nina. So let's think about what we're doing here. We want to talk about how things could flow out of the NM state and how things could flow into this NM state. So let's start with the flowing out. How can you flow out from this NM state? It's always going to start with a minus P NM of T, the probability of being in the state to begin with, and then you have to multiply by the rate of flowing out. Did you have that rate, Nina? So one way of thinking about this is our N, this is our M, right? So you're totally right, it has a beta over kappa, and then we have, perfect. Is there anything else that I can do in order to leave this state? Maddie, you're nodding, so I'm gonna go to you.
Gamma M.
Plus gamma M, right? So that's the total rate in which you flow out. You can flow into the state in two different ways. You can flow into the state by having a transmission event. Or you can flow into the state by having a recovery event. Now, this is a little bit hard to see. So I'm going to show you several different ways to think about it. One of these might resonate with you more than another. Use whichever one resonates with you the most. So if you find one of them confusing, just ignore it, and we'll use the thing that's most resonant with you. Okay, so here's one way to think about it, is that you have your focal state, which I've shown in red here, and you have two different types of arrows. You have a transmission arrow and a recovery arrow. So a transmission arrow reduces the number of susceptible hosts, which is drawn on this axis, by 1, and it increases the number of infections by 1. So it's these diagonal arrows. So it turns out that there's lots of diagonal arrows on this figure, but only one of them from here to here describes the flow into the state. Okay, so that means that we have to go from N plus 1, M minus 1 state into the NM state. So there's lots of transmission events that are occurring, but only one of those brings us into the right state. So we have beta over kappa, N plus 1, M minus 1, times the probability of being in state N plus 1, M minus 1 at time t. Another way of thinking about that, if you find the little figure confusing, is that when we have a transmission event, it's going to decrease the number of susceptibles y1, so it's going to get rid of that, and it's going to increase the number of infections by 1, so it's going to get rid of that, and we're going to end up with N and an M, which is the state that we wanted. So you can either work forward or backwards, but you have to think about how the event changes the state, and you have to think about where it could have come from to have the current state that I want. Does that make sense? It's a little hard to wrap our heads around, but the fact is that we have two things that change. Before we just looked at something like this where it was the flow in, so it was M minus 1, but now two things are simultaneously changing, so we have to consider the effect of that event on both of the states of interest. All right, so for the recovery, we have a much simpler case because recovery only changes one of the states. It changes the I state, so it's drawn by these gray down arrows. This red down arrow is this one right here, and this black arrow describes the flow in, and it's going to flow in from the state that has one more infection than we currently have. So something like that. Okay, so that is our master equation for this system. Any questions about that? the rate of flowing out is in here, and the way that you can tell that is that there's a negative sign out here. If it's flowing out, it has to be a negative. It is the rate of flowing out of this state, but it's not the rate of flowing out of our focal state. And also, this is multiplied by our focal state. This is multiplied by a non-focal state. Does that help? Okay. So, let's look at the dynamics of this system. One way to draw this is at a particular time. In particular, I simulate this up to some time t max. We can look at the state of the system in terms of the number of infections, the M and the N, and we know that the number of infections plus the number of susceptible individuals has to add up to K or less. So that's what I was talking about before, that the number, that actually everything up here is inaccessible. So you could not have actually been up there. So the probability of being in the upper triangle is actually 0, because these two have to add up to something less than or equal to K, or kappa. All right, so let's think about what the different elements of this mean. It's really, notice that most of the probability is really small. That is actually not that surprising, because there's a lot of states in here. So if you're going to have to talk about the probability and you're spreading it out over lots of different states, the probability of being in any one of these boxes is pretty small, except for this box right here, which is when you start with a single infection and that infection just goes extinct right away. So a lot of probability builds up here, a lot of probability builds up here, which is like that single initial infection infects somebody else, and then both of those go extinct. So this is the branching process region of our plot. This is the master equation focused region of our plot. Now, the master equation describes this whole area, but if we really wanted to understand what was going on over here, that's when we should use branching processes. Does that help? Okay, so let's think about this. This first column is the column where we have no infections, M equals 0. So what this first column describes is it describes the disease-free state. In this case, I equals 0, and R is equal to kappa minus S. So note that S can still be 0, in which case everybody would have recovered, or almost everybody could still be susceptible, and almost nobody had been infected and recovered. So you can still end up anywhere along this edge. So another way to analyze this process is to just look at that very first column. So this is that first column, or the extinction disease-free case. And this is the number of susceptible hosts. So this bar right here is this yellow square right there. So most outbreaks end with almost everybody being susceptible and one individual being recovered. There are a few times when the disease breaks out a little bit and then goes extinct, and then there's a very few cases where you get a substantial outbreak. Now, what happens when you have a substantial outbreak? That is this bubble, this light blue bubble down here. So to understand this light blue bubble, another way we can think about this plot is we can calculate the average number, let me write it differently. The average number of infections at time t, or the sum over all combinations of N and M, the number of infections times the probability of having that many infections. So if I look at that instead, that gives me something like this. So this is a little bit of a reminder that this figure here and this figure here are just one snapshot in time, and we can actually look at all different times on this axis, and this is the average size of the outbreak at time t. So one thing to take away from this is that analyzing these processes, even after you solve the master equation, is not extremely easy. There's so much information in the master's equation that it takes a lot of time and effort and plots to pull that information out and synthesize it. However, there are a few different ways we can think about synthesizing it. We can look at a snapshot in time across all of space. We can look at a snapshot in time along a single column, or we could look at some sort of dynamical aspect model. Does that make sense? Yeah.
And if we wait long enough, after 1,000 months, so then we wouldn't have this.
Everything would build up on this edge. Yes, exactly. All right, so just to give us one more example, let's consider the birth, death, diversification model. So diversification models are actually one really cool application of stochastic processes. So when we talk about diversity, what I mean here is how many species we have. So a birth is a speciation event. A death is an extinction event. And the way that this model works is that you consider these two different types of events, either speciation or extinction. And we're interested in n, the number of species. So following the classic notation for this, the rates at which these two events occur, the speciation rate is lambda times the number of species. So this means that the more species that there are, the faster species are created. So it's a per capita speciation rate. You also have extinction, which occurs at rate mu. So the more species there are, each species goes extinct independently, so the more extinction there is. Okay, what's the effect or the change due to, in the number of species due to each of these events? What would a speciation event do? Increase. So you'd have n plus plus, and similarly an extinction would decrease it by 1. Okay, so I'm going to give you a few minutes to write down the master equation for this system. All right, does somebody want to get me started? What's on the left-hand side of my differential equation? dpn by dt. So the rate of change of the probability of having n species at time t. All right, what's my flow out? So I always want to talk about the flow out from my focal state. So I have minus Pn of t. Then I want to consider lambda n plus mu n. So my two events that could have happened. You could either gain a species and leave, or you could lose a species and leave. All right, what happens if a speciation event occurs? How do I flow in from a speciation event? Yes, Mark.
So it would be P of n minus 1 times lambda times n minus 1.
Perfect. Because you have to flow in from the case down below you, and then you have to flow out. Or if you have an extinction event and it leads to you ending up in the class, you have to start with one too many species and lose that extra species through extinction. All right. So what is the smallest value of n that I could have? Could n be 2? Yeah, you could have 2 species. Could n be 0? So this is a little bit of a trick question because I think your intuition is right that n wouldn't be 0 because we would never study something that didn't exist. But imagine a group of organisms that have all gone extinct. In that case, n is equal to 0. That certainly has happened in the past. So n certainly can be 0. Now, there cannot be a taxa that is currently present in the extant is what we call it, that has n equals 0. But if we're considering all possible realizations of the world, n could be equal to 0. What is the biggest n could be? I love your strategy. Just pick another letter and define it as the max. I love it. In some ways, that's actually exactly what we do. So I'm going to do that. So technically, the number of species could be infinity, but obviously you could not write down an infinite number of the differential equations. So at some point, we have to pick a maximum number of species that we're going to consider, in which case we have to set n max plus 1 at all time t equal to 0. So this is an approximation to deal with the fact, like I'm missing a letter in there, but whatever. Approximation of the fact that we can't evaluate an infinite number of differential equations. So your answer was exactly right. All right. Any questions about master equations? So if you feel a little nervous about them, you can go through any of the examples that we talked about in topic number 5, and you can use that stochastic process that I described and write down the master equation. So there's lots of examples out there for you to practice with. All right. But as we've seen here, there are some pretty big limitations to master equations. First of all, they require evaluating a lot of different differential equations, possibly so many that they're impractical. Second of all, once you get the solution, they often give you so much information that it's hard to digest that information. So this begs the question, could I write a simpler set of differential equations that has a fewer differential equations that really gives me the information that I wanted to have anyway? And that brings us to lecture 5.6. The ensemble moment approximation. So remember that the master equation approach gives you a set of differential equations that describes the probability of being in a particular state at time t. The master or the ensemble moment approximation, which I am just going to abbreviate with EMA, you a system of ODEs moments so the ensemble moment approximation gives you a system of ODEs that don't describe the full probability distribution, but rather the moments of that probability distribution. I forgot to answer Mark's question. Mark asked a question earlier about when we were doing the SIR model, were we making the assumption that only one event was happening at a time? And yes, in both this approach and the master equation approach, we assume that only one event occurs at a time, and that's not even an approximation. That's not the approximate part, because we're describing differential equations, and so since events occur at a given rate, no two events can occur at exactly the same time. And so if you had a system that really did have two events that occurred at the same time, that would really be a discrete system in some way. Yeah. Did you have a question to follow up with that, Mark? Or is your hand raised from before? Oh, okay. So I'm gonna just, okay. So I'm just gonna keep going. Okay, so we're gonna complement the master equation approach that we had before with this ensemble moment approach. So in topic 1, when I first introduced moments, you would be totally forgiven for thinking, oh, this isn't a little tidbit that I will forget and never remember again. Because when am I going to use a moment? Well, this is when you're going to use a moment. So let's do a little bit of review. We had 2 different kinds of moments. We had raw moments and centered moments. So as we'll see in just a minute, the raw moments are much more natural to calculate. And the definition of the nth raw moment is that if we have a random variable x and we take the nth power of it, and then we take the expectation of it, so this is the sum over all the values of x in our sample space, x to the n times the probability that x is equal to x. This is our nth raw moment. Okay, so just because I'm a little bit of a meanie, we add one more new type of notation, which instead of using an expectation E, which can be confusing in some situations, we're going to use this bracket notation. So this is exactly the same as that. So instead of writing all these E's and having a bunch of parentheses all over the place, I'm just going to write this bracket. Okay, so those two are exactly the same. How do we express the variance in terms of raw moments? So the variance is an example of a centered moment. It's the second centered moment. How do we express the second centered moment in terms of the raw moments. So how do we take the variance and write it in terms of things that look like this? All right, so the first thing we have to do is we have to remember what the variance is. So the variance in our random variable x is equal to, and now using that bracket notation, we have x minus the mean of x squared, like that. So this is the squared deviation from the mean. The expected squared deviation from the mean is the variance. Okay. So what I really want you guys to get out of this review part is the procedure we're going to use right now. So if you don't remember anything else about this review part, please just remember this procedure. Okay, so the first thing we have to do in order to do this is we have to expand. So we currently have this quadratic term in here, and it's all mixed up, so we have to start expanding. So we have x squared minus 2x, the mean of x, plus the mean of x squared, and we want to take the expectation of that whole quantity. I just expanded what was on the inside. Okay, does anybody have a suggestion of what I do next?
Sum of some term and the expected value can be be circumcised.
Perfect. So we remember that we have some expectation rules. So the expectation rules are that you can split an expectation up on the sum, and you can take out constants from an expectation. So let's do this. So we can split up on the sum. So I have x squared plus the expectation of 2, let me take out the minus 2. We'll do it in 2 steps. X, like this, plus x squared. Okay, so there's a reason I never wrote down notation for when you have double brackets, because when I take an expectation of something that I've already taken the expectation of, it's just that quantity. So I can drop the double brackets, which means that I can take this out. And this quantity here, this expectation, is a constant. We already took the expectation of it, so it's really a constant. So I can take it out as well. So what this turns out to be is it turns out to be x times x, which of course is x squared. So if it ever confuses you, you can always exchange these things for a mu, and then mu is a constant, mu can come out. All right, so notice that this simplifies to being x squared minus x squared.
So
Yes.
the previous line should be the expected value of x squared. Right.
Oh, thank you, thank you. That's important. Thank you. Okay. So we have x squared minus the expectation of x squared. So that is the definition of the variance. So we use moment rules, or expectation rules, sorry. Expectation rules. To simplify. All right. So that's all the review about moments. Now, there is one simple rule to doing this whole ensemble moment approximation. The EMA follows from the following. The rate of change of the expectation of some quantity x And this quantity x that I put in here, this x is pretty arbitrary. This could be, for example, using our examples from before, could be the variable n. It could be the variable of n squared, or in something like the SIR model, it could even be n times n. So x is a stand-in for any combination of random variables or function of random variables that we care about. Okay? This is equal to the expectation over all of the different events that occur, the rate at which event E occurs, and the effect of event E on the random variable x. So when I write delta E of x, what I mean here is x after the event minus x before the event. So final minus initial. Importantly, if I have, for example, n squared, this is n after squared minus n before squared. This does not equal, so a big does not there, does not equal n after minus n before squared. Okay, so that is not true. This is what we mean. So it's the change in this quantity x due to the event, so we have to take the whole quantity after minus the whole quantity before, not the change squared. Okay, so as a simple example of this, let's use that birth-death process that we just had up above. So we had speciation and extinction. And this is one reason I like writing this as a table like this, because I'm going to now just exchange this for n plus 1 and n minus 1. Those are my n afters. Then I can subtract the thing before and I get my change. So that I have here the rate of change in the mean number of species is the expectation over the sum of the different events that I could have. The first one is a speciation event, which occurs at rate lambda n. Then I have the effect of the speciation event, so I have n after minus n before, plus if I had an extinction event times the effect of an extinction event, which is n minus 1 minus n. Okay, so this n is going to cancel with that. This n is going to cancel with this. And I get that this is equal to the expectation of lambda n plus mu n. All right. So we can still apply our expectation rules just like we did up above for the variance. So we have d by dt of n is equal to lambda plus, oops, sorry, there should be a minus sign. I missed this little minus sign right there. Lambda minus mu times the expectation of n. So this tells us that the expectation of n satisfies this differential equation. Does anybody recognize this differential equation? Don't think about it specifically. Think about it generally. How would I solve this? It's an exponential, right? It's just the classic per capita growth. I have the change in the number of individuals and some constant times the number of individuals. You could do separation of variables and you could solve this and you would get that the expected number of species, the average number of species, is equal to the initial number of species, e to the lambda minus mu times p, where this is a function. This is really cool. This tells us that if we have random speciation events and random extinction events, on average, the number of species that we have in our system is described by what we would really want to describe it by, which is the exponential growth or decay of the number of species, depending on if the speciation rate is bigger or less than the extinction rate. I think that's really cool. Okay, but we can even go even further. We may not quite get done with this, but we can talk about not just the expected number of species, but the variability in the number of species by asking the question of what is dn squared dt. Okay? So I want you to keep that equation in mind that we had right here. So let me try to extract this equation. So this is our focal equation that we have to follow. And we're going to do the same thing, but we're going to put in n squared for x. So I have to take the expectation. I want to sum over the number of events. I only have two different events occurring here. I have the speciation rate and or speciation events and extinction events. So let's consider speciation first. We have lambda times n. That's the rate at which speciation events occur. Then I want to say, what is n squared after a speciation event occurs? Minus n squared before the speciation event occurred. So after the speciation event occurs, I have n plus 1. I want to square that, and I want to subtract it from the square of the number before the speciation event occurred, plus this other type of event, which is an extinction event. Then I want to do n minus 1, that's the number of species after an extinction event, square that, minus the number of individual or species before extinction squared, and take the expectation. So this whole method is just a method of very systematically following the rules. All right, so let's, just like we did above, we have to expand and simplify and separate things into terms before we can use our expectation rules. So let's simplify this. This is n squared plus 2n plus 1 minus n squared. So it ends up being 2n plus 1. And then we have n squared minus 2n plus 1 minus n squared. Those guys cancel, so we have 1 minus 2n. So simplifying here, we have lambda n times 2n plus 1 plus mu n times 1 minus 2n, like that. All right, so I'm going to go one more step before the end of class. So we still aren't to a point where we can use our expectation rules because there's still parentheses on the inside. We have to be able to break up on sums. And so let's expand this just a little bit more. We have 2 lambda n squared plus lambda n plus mu n minus 2 mu n squared. Or one way of thinking about this is that you have 2n squared lambda minus mu plus n lambda plus mu. All right, so this is where I'm going to pause for now. Between now and Friday, when we resume, take a few minutes to think about how you would apply your expectations. Okay, and then I'm going to give you one more challenge. You can choose to do this or not, try to figure out what the rate of change in the variance of n would be. If you remember, this is equal to d by dt of n squared minus n squared. So this is equal to d by dt of n squared minus d by dt of n squared. Okay, so I will leave you guys with that, and we will go and practice it next time, so don't worry if you can't get to it, but it's one thing for me to tell you and another thing for you to try. So give it a try and it might really make this solidify in your brain. Okay, I'll see you on Friday.